So we're here now to sort of wrap up our discussion of alphane modes. Well, to be precise, modes in a magnetized plasma, okay, which include alphane modes as well as the alphane modes plus fast and slow magnetosonic modes. Okay, and so just to reiterate, the alphane mode is very much like a wave on a string. So that would be a stretched string, which is essentially the magnetic field line here, and you twang the string like this. You have transverse displacements, transfers to the direction of the string and also to the direction of propagation, and the string starts exhibiting undulations like this, and the wave travels in this direction with a velocity VA, which is b squared over a for pi over rho. This might be 4 or 8. I'm not entirely sure. Please check. And these would be the alphane waves. They are transverse waves with no density perturbations. However, these two modes, the fast and the slow magnetosonic modes, which we have discussed at length, they are sound-like waves, okay, and they are a little complex. It all depends upon the precise characteristics, depend upon the direction of propagation with respect to the background magnetic field, and that's true for the alphane mode also. Dispersion relation is omega square equals kz squared Va squared, okay, where the kz is essentially k cosine theta. The theta is the direction between the k vector and the direction of the magnetic field. So that is true for the alphane wave also. The fact that the propagation is anisotropy, well, that the theta matters. But let us now, since the magnetosonic waves, the fast and the slow magnetosonic waves were slightly different, let us summarize, having discussed them so far, let us summarize their properties a little bit. First of all, the main thing is the ratio of the alphane velocity to the sound speed. This matters. This matters greatly. Or if you will, you can equivalently the ratio of VA to CS, and you can also write it in terms of the plasma beta. Okay, I leave you to figure out how. If you remember, the plasma beta is essentially the ratio of the magnetic pressure to the particle pressure, gas pressure to the magnetic pressure. Okay, so when the beta is very low, that means the magnetic pressure dominates, and when the beta is high, the gas pressure dominates. And I leave you to figure out the relation between beta and VA over CS. Okay, it's quite easy. You can just go from here and figure this out. Anyhow, so the deal is for low beta, for beta greater than 1, okay, in other words, VA over CS less than 1, okay, the fast mode, when I say fast mode, I mean fast magnetosonic mode, okay, it is almost like a sound wave, almost like a sound wave, okay, modified a bit by magnetic pressure. Almost like a sound wave, except it's modified by b squared over 8 pi, modified by the magnetic pressure. Okay. For beta less than 1, in other words, V over CS greater than 1, yeah, it propagates the speed the speed of the fast mode is so right now we are discussing only the fast mode. Okay, we will after this we will discuss a slow mode. Okay, the speed is almost the alpha in velocity. Okay, and the fluid displacement displacements are perpendicular to the magnetic field, very much like the alpha in speed. Okay, but it's almost isotropic. In other words, the dispersion relation, the dependence of this of omega and k does not contain a theta, as in the dependence on theta is very weak. Okay, so in these two, as in the beta less than 1 limit, it is like the alpha in waves in these two respects, in that it propagates at the speed at the alpha in speed almost, and the fluid displacements are also perpendicular to b, so it starts looking like a transverse alpha in wave. However, the dispersion relation is such that the theta dependence is very weak, unlike the case for an alpha in wave, which the dispersion relation does have a very strong theta dependence. Okay, and for the fast mode, the group velocity, which is the velocity at which the energy propagates, the energy always propagates isotropically, not along the field or perpendicular to the field, propagates almost isotropically regardless of beta, regardless of beta, or regardless of the ratio of VA over CS. Okay, so that completes our little wrap up of the fast mode. Now, by the way, all of these relations, all of these deductions simply follow from the dispersion relation that we have seen earlier. Okay, what I'm saying here is nothing. It's simple. You stare enough at the dispersion relation, you will be able to figure all these things out. Okay, these are just sort of all these things that I'm telling you right now are just convenient, markers to maybe to remember. But other than that, everything is contained in that dispersion relation that comes out of the quartic equation that we've seen earlier. Okay, now as regards to slow mode, so from now on, everything that we will be saying has to do with the slow mode. Okay, as regards to slow mode, at low beta, it behaves like a sound wave 1D. It's like a 1D sound wave, except it's not isotropic. Sound waves are isotropic, guided by the field. Okay, so it is very much like a sound wave in many respects, in that the propagation speed is almost the sound speed and so on and so forth, except it's not isotropic, it's guided by the field. Okay, at high beta, in the other limit, at high beta, it starts looking like a alpha in wave, in that displacements, i.e. what I mean by that is that displacements, the fluid displacements, are perpendicular to the field, perpendicular to B, okay, perpendicular to the wave vector, actually perpendicular to, strictly speaking, I really should say wave vector, perpendicular to K, to the wave vector. Okay, and regardless of the beta, okay, the energy, the group velocity d omega dk, the energy always propagates along the magnetic field. Propagates along B. Okay, this is how. So you notice the big difference between the slow mode and the fast mode with regard to energy propagation. For fast modes, the energy always propagates isotropically regardless of beta. Okay, in other words, it has nothing to do with the magnetic field. Whereas for the slow mode, regardless of beta, the energy always propagates along the magnetic field. Okay, so this completes our short survey of the different modes of propagation in a magnetized plasma. Okay, so now you might ask, okay, all of this is fine. We talked about the sound wave, we talked about the Alfvén wave, we've talked about two kinds of magnetosonic waves. Now, what about it? I mean, in practical terms, why is it important in astrophysical studies? Well, really, one of the reasons this is, I can give you a couple of answers to that. One is many times these waves are important. It's important to identify the waves, okay, because any arbitrary disturbance is really a superposition of waves. Okay, it's a superposition of waves. It's just not just one kind of wave or the other. Many times there can be a mix of waves. So it's important to identify the dominant kind of wave. That's one thing. The second thing is waves dissipate, although in this case we're talking about ideal MHD, so there's no scope for dissipation. But nonetheless, in non-ideal cases where finite resistivity is present or finite viscosity is present, waves do dissipate. Okay, and the dissipation leads to heating of plasma. And this is often a very important question in astrophysics. For instance, the heating of the solar corona, of the outer atmosphere of the sun. This is after, like, shall we say, 2 decades of research. This is still an unsolved problem. And so it's important to know many times, people resort to the existence of different kinds of waves in order to understand how the solar corona is heated. Well, dissipation mechanisms apart, in the first place, you need to identify which kinds of waves are you talking about, and so which kinds of waves are you holding responsible for the dissipation. Okay, so this is one reason we need to understand waves. Okay, the other reason, of course, are shocks. As we've said, shocks are very, very important in astrophysics, and so shocks / discontinuities, right? So the question is, what kind of shock are we talking about? Are we talking about, for instance, a sonic shock? A sonic shock meaning a sonic shock arises from a situation where a piston or a driver or some object exceeds the speed of sound, and that can possibly lead to steepening, nonlinear steepening, and the formation of a shock. So what was the characteristic speed? The object, this can happen when an object moves at a speed greater than the sound speed. Similarly, you might, now that we've identified 2 or 3 other kinds of speeds, 3 other kinds of characteristic speeds, you might say that in this case, or in the CFMS or CSMS. So all of these are now characteristic speeds. This refers to the fast magnetosonic speed, and this refers to the slow magnetosonic speed. So now if instead of just one kind of shock, you have the possibility of all kinds of different kinds of shocks. Okay, so again, why is this important? Well, it's important because, if you're talking about most of the time, as we've seen, as we've discussed, in astrophysics, you hold shocks responsible for particle acceleration. Right? And if you're going to be holding it responsible for particle acceleration, you need to know what kind of shock you're talking about. Only then you will know what kind of jump conditions you to expect, and then you can go on from there. Okay, so because things depend upon the jump conditions, apart from the intrinsic interest in knowing what kind of shock it is, right? And now, having identified 3 more characteristic speeds, we know that there can be many different kinds of shocks. There can be a sonic shock, there can be an alphanic shock, there can be a fast magnetosonic shock, there can be a slow magnetosonic shock. Sometimes an object can exceed more than one of these speeds, and then the question is what kind of shock will form, what kind of shock is most likely to form. Okay, so now these are fairly involved questions, and we cannot possibly, I just wanted to motivate it, and we cannot possibly go into the details of all of these, but I will try to sketch some of these details, some of these issues before we go on, or at least give you at least some idea of what to expect from the fact that we now have several different kinds of characteristic speeds. Okay. So before that, just by way of very quick review, how does a shock form? The shock forms, suppose you have a pressure pulse, right? And we're simply talking about hydrodynamics now. We're simply talking about how hydrodynamic shock forms. So this would be a pressure pulse in X. So here what happens is, simply because the pressure here is larger than the pressure here, the sound speed here, CS1, is greater than CS2, right? So the crest, so the crest starts overtaking the leading edge, so it starts doing this. Okay, and so eventually there is steepening, and like that. So eventually what will happen is when the crest starts over, simply because the sound speed is here is larger than the sound speed here. Why is that? Because the pressure here is significantly larger than the pressure here. These are not small amplitude waves. These are there's not a small amplitude disturbance. Rather, there's a large amplitude disturbance. Okay, so the wavefront steepens. This steepens, and a shock may form. So this would be the steepening of the wavefront and a possible formation of a shock. And so this was like a 1-slide review of when a shock might form, and then what we did for sonic shocks was we wrote down the shock jump conditions. In other words, what to expect on either side of the shock, right? We used the mass, momentum, and energy conservation equations to figure this out, right? To figure out the jump conditions. In other words, how much of a jump to expect in various quantities like density, pressure, velocity, and so on and so forth on either side of the shock. Now we've done this earlier, but I thought I would introduce this to you in slightly different language. For instance, when we employed mass conservation, we said rho 1 U1 is equal to rho 2 U2, where the ones represents the upstream condition, 2 represents the downstream condition, so on and so forth. We did this, and we so this is essentially what we did. And when we conserve momentum, we said rho 1 U1 squared plus P. I urge you to go back and look at this. This is rho 2. U2 squared plus P2. This is how we did it, right? And when it came to energy, so now another way of writing this very same thing is to say that, now first of all, we take the shock propagation direction to be x. Just for simplicity, this shock is propagating in the x direction. Now, Mass conservation can be written as, there are these two, this is just notation. Okay. This is the same as this. Okay. So this is what so instead of writing this, I might simply write okay, which is to say, this is simply to say that rho 1 ux1 minus rho 2 ux2 is equal to 0. That is what this notation is telling you. The reason I am saying this is I just wanted to introduce this notation here. That is all. Okay, and nothing different. So for sonic shocks, mass conservation can be written as that, and momentum conservation, can be written as rho ux squared plus p equals 0. Again, this is the same as this. Okay. So far we are not saying anything new, we are simply reviewing what we have already done. Okay. We're just yeah. So there is nothing terribly new in what we are saying here, and for completeness the energy conservation is written as this. Can be written as rho, and now we are introducing a new quantity. This is nothing different from what we've seen earlier. I'll explain this in a minute. Plus it just looks different, it's really the same thing, where I is what's called the internal energy density, and is equal to P over gamma minus 1 rho. That's the definition. Okay. So now what we've done so far is simply write down the mass, momentum, and energy conservation for a hydrodynamic shock, and from the mass, momentum, and energy conservation equation, we can figure out the jump conditions. The jump conditions rho 2 over rho 1 was equal to I will simply write this once and write one of these expressions and then leave it there. This is simply a review. I don't want to repeat everything now. This is just to make you familiar with the previous result. In the same spirit as what we did, we first reviewed sound waves before going on to alphane waves and fast and slow magnetosonic waves, right? So it's in the same spirit. We are now reviewing sonic shocks, which we've already done before going on to other kinds of shocks. Okay, so now these jump conditions, this for instance, the ratio of the densities is given by this. This comes from the conservation relations, and which are those? The conservation relations are just these. Are this, and this. So just like the density jump conditions, you also have the velocity jump conditions, v2 over v1 for instance, the pressure jump conditions, so on and so forth. Okay, so this was just to sort of give you an idea, and so M of course is the sonic Mach number equal to velocity over just the speed of sound. Okay. So now, as you can suspect, with the other kinds of characteristics speeds, which is the alphane speed, the slow and fast magnetosonic speeds, you will start having different kinds of Mach numbers also. Not just a sonic Mach number, you will have an alphane Mach number, you will have a slow magnetosonic Mach number, you will have a fast magnetosonic Mach number, right. So, things start getting a little more complicated, but that's okay. I mean, it's nothing to, you know, the philosophy is still the same. Okay, so it's on that kind of philosophy that we focus right here. Now, from hydrodynamics, while going from hydrodynamics to magnetohydrodynamics, okay, what happens? What changes? Well, as we've said, as we've remarked a few times earlier now, there are 3 more characteristic speeds that happen. But as far as conservation relation goes, okay, these conservation relations that we just wrote down, what changes? Well, mass conservation is unchanged, thankfully. Unchanged. It's the same as what it was, you know, for hydrodynamics, even when you do magnetohydrodynamics, right? Momentum conservation. Well, what was new in the momentum conservation equation when we did magnetohydrodynamics? Momentum conservation. You remember that while talking about momentum conservation, the one thing that that was new was you need to add the Lorentz force, the J cross B force, right? So this is the new thing. That's the new wrinkle, or the new complication, if you will, when you start doing magnetohydrodynamics, right? And also, so energy conservation. Well, energy conservation, you need to include magnetic energy. Magnetic energy density. Okay, so that's one thing. Also, additionally, since we are dealing with electric and magnetic fields, you need to consider the divergence of B equals 0. You need to consider, right, and consider conservation. So you need, this is a divergence constraint. And conservation of magnetic flux, which comes from the induction equation, of course. Conservation of magnetic flux. So, in addition to mass conservation, which is unchanged, momentum conservation, which is technically the same equation, except we need to add Lorentz forces. Okay, again, also with energy equation, which is pretty much the same, except we need to include magnetic energy density. We also have 2 new constraints when we are dealing with magnetohydrodynamics. One is the divergence constraint, which is the divergence constraint on B, and we also need to take into account conservation of magnetic flux. So you have to take these 2 new things plus the extra bits in the old conservation equations into consideration when trying to derive jump conditions in magnetohydrodynamics. Okay, so that's it for the time being, and when we resume, we will start writing down the conservation conditions for magnetohydrodynamics. Thank you for now.